Alright, hello class. In this video we're going to be talking about LHopitals Rule. I know that this name can seem intimidating. It's very French, but it's my understanding that this is pronounced l'hôpital, alright, which I sort of just say l'hôpital. So LHopitals Rule. And this is a rule that is an application of derivatives to limits. Now, there's a big problem when people try to use this before we talk about derivatives, because you need limits to define derivatives in the first place. So you can't use it if you are trying to find limits to help you find derivatives, right? It becomes this sort of circular problem. However, now that we've done all this work with derivatives, we can actually use derivatives to help us find more complicated and maybe not even so complicated limits. Okay, so let's describe how it does that, show where it comes from, why it works, and also we need to talk about that this will not work for every type of limit you might find, but in the end it's really okay because it does help with the majority of the limits that would ever give us problems. Alright, so here's what LHopitals Rule says. And there's a lot of setup here, but essentially what you need to know is the functions we're talking about need to be differentiable, and it needs to be a 0 over 0 case. Okay, but that's what all this is saying. So we're going to suppose that f and g are differentiable on an open interval I containing a with g prime of x not equal to 0 on I when x is not equal to a. So we just can't let g prime of x be 0 like more than at just one little point a. Okay, so if the limit as x goes to a of f of x is equal to 0 and the limit as x goes to a of g of x is 0, then the limit as x goes to a of f of x over g of x, so this would be a 0 over 0 case here, because we've already said that f goes to 0, g goes to 0. So this is a 0 over 0 case. Given that, we can instead look at the limit as x goes to a of f prime of x over g prime of x, right? Provided this limit on the right exists or is plus or minus infinity. Now, this rule also applies if x goes to a is replaced with x going to a from the right side, the left side, or even a plus or minus infinity. And even more, this rule actually also works for a infinity over infinity case. All right, so here's the big idea, the big takeaway. For 0 over 0 cases, okay, or infinity over infinity cases, so really the big indeterminate forms that we have, right, if you have f over g, you can instead look at f prime over g prime. Okay, and you'll notice I'm putting a little h over the arrows or the equal signs, and that's just to let me know that I'm using LHopitals Rule. I'll talk about that in a bit when we start looking at examples. All right, but these are the big takeaways here, that in these two main indeterminate forms, we can instead look at the derivative of the top and the bottom, if that will help us find the limit. All right, now this is typically used for situations where we can't rely on the techniques that we used in the past. This is helpful for when algebra isn't going to apply. Okay, so while it's helpful for situations when algebra won't apply or won't really help us, it can still be used in those cases. So let's look at an example that we already know how to do and see if LHopitals Rule applies. Okay, so for example, take the limit as x goes to 1 of x squared minus 1 all over x minus 1. This is one of the first limits we looked at, and it's a 0 over 0 case. All right, so using the techniques we already know, we would just factor and cancel, right? We'd get x plus 1 times x minus 1 up top The x minus 1 in the bottom sticks around but cancels. And now we should be able to just plug in the 1 because we've reduced this down to just x plus 1. So we end up with 2. Okay? So this is with algebra. Okay? Let's look at it with using LHopitals Rule. Okay? So setting this up with LHopitals Rule, once again, it's a 0 over 0 case. All right? And what we can do instead of looking at this limit is we can look at the limit of the derivative over the other derivative, right? So it could be the derivative of the top, which will be 2x, over the derivative of the bottom, which will be 1. And I always mark my limit with an h when I'm using LHopitals Rule, just to let everyone know, readers, myself included, that we are looking at LHopitals Rule. And so now we could really be thinking about the limit as x goes to 1 of 2x, which ends up being 2. All right, we get the same answer. All right, now I do want to note that this will not always work. So if we instead looked at the limit as x goes to 1 of, let's say, x squared minus 1 over x plus 1, so notice this is no longer a 0 over 0 case, right? Because we can just plug in the 1 and get 1 minus 1 over 1 plus 1, so we have 0 over 2, which is 0, right? But if we were to use LHopitals Rule, right, when we take the derivative of the top, we get 2x again, and derivative of the bottom is still 1. So we actually end up getting 2 again. Okay, so LHopitals Rule definitely does not work if it's not a 0 over 0 case. However, if it's not a 0 over 0 case, you don't really need to worry about it, because the only possibilities you would really have are you just plug it in and you get a number, or you get a plus or minus infinity case. And those, you know, we have a pretty straightforward way to deal with those as well. Okay? All right, a fair question here is, well, why does this work? How does this work? It seems like too good to be true, right? Well, here's how it works. If you have the limit as x goes to a of f of x over g of x, and everything's differentiable and continuous, that means you're going to have f of a over g of a, and we're saying that this is a 0 over 0 case, right? So that means that f of a equals 0 and g of a equals 0. All right, well, if we start on the other side of the equation, right, if we start here with the just f prime of a over g prime of a, okay, well, and this isn't also, say, a 0 over 0 case, right? This actually comes out to be some number. If we look at the definition of the limit here, well, we could add in the limit as x goes to a of f of x minus f of a all over x minus a all over the limit as x goes to a of g of x minus g of a all over x minus a. Okay, and these x minus a's are going to cancel because we can bring them out as a 1 over x minus a over 1 over x minus a, right, like so. So here I move the limits outside of the fraction like this. So we have the limit as x goes to a of f of x minus f of a all over g of x minus g of a, and then we have the 1 over x minus a all over 1 over x minus a, and this comes out to just be 1. But even more, we already said f of a is 0, g of a is 0, so this comes out to be, all right, then we get down to the limit as x goes to a of f of x over g of x, once all this simplifies out. And then this, well, as I said, if we're assuming that f prime of a and g prime of a are, exist and aren't 0 over 0, This is actually the limit as x goes to a of f prime of x over g prime of x. Okay, so this is basically how it works on the 0 over 0 case. There's some other things to consider here, but this is overall why it works. Now, let's talk about where this is most useful. It's, of course, in places where we cannot factor and cancel, we cannot use conjugating factors, or in cases where we just don't want to, right? So let's just look at a few examples of this in action. And okay, so here's an example. Say the limit as x goes to 1, the natural log of x over x minus 1. This is going to be a 0 over 0 case because the natural log of 1 is 0 and 1 minus 1, of course, is 0. So it's a 0 over 0 case. So, and it's also one where algebra is not really going to help us. We can't really factor or cancel or do much here to simplify this expression to make calculating the limit easier or even possible necessarily. So what we do is use LHopitals Rule. Okay. So with LHopitals Rule, we take the derivative of the top. Now, keep in mind, with LHopitals Rule, we are not doing the quotient rule. We're not taking the derivative of the entire thing. We take the derivative of the top, which in this case will be 1 over x, and it's over the derivative of the bottom, which is 1. Okay, so this is the limit as x goes to 1 of 1 over x, which is 1. Okay, and there we go. It's that simple. I think students, after all of these applications of the derivative that you fight through, like related rates and optimization and stuff like that, I think LHopitals Rule actually feels kind of nice because it simplifies something that used to give us a big headache early on, right? Those limits were things that I think some students don't like doing. But with LHopitals Rule, they become a lot nicer to work with. All right, so for our next example, let's say we have the limit as x goes to 0 of e to the x minus 1 all over x squared. So when we plug in 0, we'll get 1 minus 0 minus 1, so it's 0 on top, and then 0 squared on the bottom. So it is a 0 over 0 case. Again, that's something we do need to check because this won't work if it's not a specifically 0 over 0 case. All right? So then, once we have that 0 over 0 case, we can apply LHopitals Rule. So we'll take the derivative of the top, which will be e to the x minus 1, over the derivative of the bottom, which will be 2x. So let me write the limit sign again. So now we have the limit as x goes to 0 of e to the x minus 1 all over 2x. Now here's where some of you may start to worry. Because when we plug in 0, we're going to get 1 minus 1, which is 0 over 0. So we have another 0 over 0 case. That's okay. We can apply LHopitals Rule multiple times until we get down to a final answer, right? And this is what makes LHopitals Rule so powerful because we can just keep applying it until we get something or things fall apart, right? So if we apply it again, we'll take the derivative of the top. Let me write my limit thing again. Take the derivative of the top, which this time will be e to the x, and the derivative of the bottom, which will be just 2. Now, when we plug in our 0, we will get e to the 0, which is 1 over 2, and there's our final answer. Okay, so don't be afraid of applying it multiple times. Provided you still have a 0 over 0 case, you can just keep going until you don't have a 0 over 0 case anymore. Okay, as mentioned earlier, this will also work for infinity over infinity cases, which is what we have here. The limit as x goes to infinity of 4x cubed minus 6x squared plus 1 all over 2x cubed minus 10x plus 3. We already know, based on what we've seen before, that using our older methods, this would just be the limit since we're doing an infinite limit, we can just look at the leading terms. So this will be the same as basically looking at 4x cubed over 2x cubed, and the whole thing comes out to be 2. So this function has a horizontal asymptote of 2. Now, this, I think, is still the most efficient way to do this. But if we apply LHopitals Rule, okay, what we will see is we will get the same answer, but it may take more work to get there. Okay, so first of all, this is an infinity over infinity case. That is another indeterminate form. So applying LHopitals Rule, this will be 12x squared minus 12x on the top, and on the bottom we're going to get 6x squared minus 10. And this is still an infinity over infinity case. Okay, so if we apply LHopitals Rule again, okay, we're going to have 24x minus 12 on the top, and we'll have 12x on the bottom. And since x is still going to infinity, this is still an infinity over infinity case. Okay, so I should say I was using LHopitals Rule there. So we can apply LHopitals Rule again to finally get the derivative of the top, which will be 24, over the derivative of the bottom, which will be 12, which comes out to be 2. So as we can see, we do get the same value. It's just a much longer process, right? So I don't recommend LHopitals Rule for everything. Okay, you'll especially see that in these infinity over infinity cases. If it's a polynomial over another polynomial, your best bet is to just use the techniques we've already learned. Okay. However, there are certainly cases where this is going to be LHopitals Rule is going to be the better option, the much better option. For example, say we have the limit as x goes to 0 from the positive side, the natural log of x over cosecant of x. Okay, well, 0 from the right, so natural log of 0 blows up, right? So in this case, this is going to negative infinity. Oops. Okay, and then cosecant going to 0, well, cosecant is 1 over sine, right? And 1 over sine, as we go to 0 from the right side, this is going to 0 from the positive. This is going to 0 from the positive side, so this should be a positive infinity. Okay, so this is an infinity over infinity case. Whether it's plus or minus doesn't really matter that much, so we can use LHopitals Rule. Okay, so LHopitals Rule, well, we take the derivative of the top, so that's going to be 1 over x, all over the derivative of the bottom. So the derivative of cosecant x is negative cosecant x cotangent x. All right. Now, before we go much further, I'm going to simplify this a little bit, because I don't like this fraction over fraction, and I kind of want to move this to be something a little nicer looking in terms of the trig functions, right? So this 1 over x is one thing, but here the cosecant x is 1 over sine of x, and the cotangent of x is cosine x over sine x. Okay, so we can invert and multiply our fractions here to get 1 over x times, so when we invert and multiply here, we'll have sine squared x on top and cosine on bottom, and I'll move the negative outside. Okay, now we are looking at, I'm going to write my limit sign again here. So we have the limit as x goes to 0 from the right of sine squared x all over x cosine x. All right, now this is going to be a 0 over 0 case. Okay, because sine of 0 is 0, and then x being 0 here makes this 0. So notice that we started with an infinity over infinity case, but now it's turned into a 0 over 0 case. But that's okay. We can apply LHopitals Rule again. Okay, So applying L'Hopital's rule again, we'll have the derivative of the top, so sine squared x, using the chain rule, that's going to be 2, and I left out the negative here, didn't I? Sorry about that. So I'll put the negative up here. It'll be negative 2 sine x times cosine x. Right? You bring the 2 down, sine to the 1 times the derivative of sine, which is cosine. Okay? Then this is going to be a product rule. So it would be the derivative of the first, which is 1, times the second left alone, plus the first left alone times the derivative of the second, which is going to be negative sine. So this will be cosine x minus x sine x. Okay? Now we're looking at the limit as x goes to 0. Now here though, when we plug in the 0, sine of 0 is 0, so the top will be 0. However, the bottom is not going to be 0, so we no longer have a 0 over 0 case. So we can just plug in the 0 to get 0 here, all over cosine of 0, which is 1, minus 0 here. So the whole thing comes out to just be 0. Okay, so hopefully that is a good example of the fact that, well, one, we can use L'Hopital's rule multiple times, but it doesn't always end up being the same case at each step. Okay, it can swap back and forth. All right, so while this seems really nice, right, L'Hopital's rule seems incredibly strong as far as the possibilities it allows for, unfortunately, it's not always going to work. So if we take this example, say the limit as x goes to infinity of x over the square root of 1 plus x squared, if we were to use L'Hopital's rule, which we technically can because this will be an infinity over infinity case, okay, but if we use L'Hopital's rule, the derivative of the top is going to be 1, while the derivative of the bottom is going to be 2x over 2 times the square root of 1 plus x squared. Right, so the 2's will cancel, and then when we invert and multiply, right, we get the square root of 1 plus x squared all over x. And this is another infinity over infinity case. Right, so if we use L'Hopital's rule again, well, the top will become 2x over 2 times the square root of 1 plus x squared, while the derivative of x will become 1. So once the 2's cancel, hopefully you see that we're right back to where we started. So L'Hopital's rule will continue to repeat this problem over and over and over and over again. This will never terminate. All right, so instead, this is the example where we do the sort of factoring out the lead term kind of idea. Because what we can do is instead say, well, this is x over the square root of x squared, which remember is our x over absolute value of x. Okay, so this is going to go to 1, and if we were looking at x going to negative infinity, it would go to negative 1 because we have that absolute value guy sitting there. Okay, so we still do need to know our previous techniques. Maybe just not use them as much as we did before. And as we've seen, sometimes L'Hopital's rule takes way longer to get to that answer than our old techniques. All right, so a natural question from this point is, well, what about other indeterminate forms? Can we apply this rule to other cases? So, for example, two of the other natural ones that come to mind would be something like 0 times infinity, right? Because which one goes there faster determines what's happening. Or, say, an infinity minus infinity. This could be going anywhere depending on which one's going faster. Okay? Well, it turns out that we can use L'Hopital's rule on these cases. We just have to rewrite what they look like. Okay, so if we can rewrite them in the form of a fraction, like 0 over 0 or infinity over infinity, we should be able to still use L'Hopital's rule. And the quickest way to show that, if you have 0 times infinity, right, and you rewrite this as a 0 over 1 over infinity, right, you kind of move this down as a 1 over infinity. You do the opposite of invert and multiply. 1 over infinity is 0, so this does turn into a 0 over 0. Okay, or you could go the other way and make this infinity over 1 over 0, right? Put that in the denominator, because when you invert and multiply, you get back to 0 times infinity. And 1 over 0, we know that that is a plus or minus infinity case. So this one, for sure, we can do this with a bit of a rewrite. We should always be able to do that. Okay, so I think it'll be easier to see if we just look at an example. All right, for a first quick example, let's say we have the limit as x goes to 0 from the right of x times cosecant x. Well, in this case, x is of course going to 0, and cosecant x, well, that's 1 over sine, and sine is going to 0, so this is a 1 over 0, which is so a 0 times a plus or minus infinity. Okay, so this is a 0 times infinity case. Now this one, I think, is a lot simpler maybe to see how you would change this into a fraction, because cosecant x is 1 over sine of x, right? And so rewriting this as the limit as x goes to 0 from the right of x over sine of x, well, now it's a fraction and clearly a 0 over 0 case, and it's so much simpler than what we started with. So now we have a 0 over 0 case, and so we can apply L'Hopital's rule. All right, so applying L'Hopital's rule, derivative of the top will be 1. The derivative of the bottom is going to be cosine x, and now we can just plug in the 0. So cosine of 0 is 1, so we get 1 over 1, which is 1. Okay? So while it might be a little simpler here, because we already know that cosecant can be written as 1 over sine, this is a similar idea to what we are always doing, as in we're going to try and put one of the pieces in the denominator. Like this example here. Say we have the limit as x goes to infinity. All right, so let's take a look at this next example here. We have the limit as x goes to infinity of x squared times sine of 1 over 4x squared. Okay, so the x squared is definitely going to infinity. All right, and then here, the 1 over 4x squared, well, that's a 1 over infinity. So what's going on inside here is it's going to 0, and sine of 0 is 0. So this whole thing here is going to 0. Okay, so this is an infinity times 0 case. Okay, so the idea here is that we are going to sort of rewrite things as a fraction. Now there are two ways we could go about this. One way is to take that x squared and put it underneath as an x to the negative 2, because then this would be a 0 over 0, because we would have sine of 0, this part's still going to 0, and this is 1 over x squared as x goes to infinity. That's also a 0. So this becomes a 0 over 0 case. All right, so that would make this a 0 over 0 case if we did it this way. Another way you could go about it is, like we did before, is move the sign down and turn it into a cosecant. Right, so we could make this x squared over cosecant of 1 over 4x squared, and that would turn this into an infinity over infinity case. All right, so which way you decide to go is not really going to matter that much. It should work either way. However, I will say that I'd much rather deal with the derivative of sine than I would of cosecant. Okay, so I'm going to look at this version of it with the 0 over 0 case. Okay, so here I've rewritten the problem a bit. we now have that this is the limit as x goes to infinity of sine of 1/4 x to the negative 2 all over x to the negative 2. Okay, and it's a 0 over 0 case, so we can apply LHopitals Rule. All right, so when we apply LHopitals Rule, well, the derivative of sine of stuff is going to be cosine of that stuff times the derivative of the stuff. So the derivative of the stuff, in this case, when we bring the negative 2 down, we'll get a negative 1/2 times x to the negative 3. Okay, and then this will be all over the derivative of the bottom, which will be negative 2 x to the negative 3. And this is sort of why I rewrote everything as negative exponents, because now, hopefully, it's fairly clear that these x to the negative 3 powers will cancel. All right, and now we should be good to go to just sort of simplify this. These negative signs will cancel. The 1/2 I could bring out and make this a cosine of 1 over 4x squared all over 4. Okay, so now that we're here, we should be able to just sort of plug and chug, because we're letting x go to infinity. So this is 1 over infinity in here. So this in here is going to 0, which means the whole top is going to cosine of 0, which is 1. Right? So this is cosine of 0, which is 1. So the whole thing is going to 1/4. And there we go. We have our final answer for this sort of nasty looking limit. All right, let's talk about rewriting things to make things look a little better for us. So let's take this limit here. Say the limit as x goes to infinity of cosecant of 1 over x all times e to the 1 over x minus 1. Now, as x goes to infinity, right, 1 over x goes to 0. So if we wanted to, we could rewrite this problem with a limit in terms of 0. Right? Because, well, as x goes to infinity, 1 over x goes to 0, and the only real x's we have are these 1 over x's. So instead, we could let u be 1 over x. So as x goes to infinity, u goes to 0. So we could rewrite the limit using u. Okay? Because if we do that, well, the cosecant of 1 over x is going to be cosecant of u. E to the 1 over x is just going to become e to the u. The minus 1 stays the same. And instead of the limit as x goes to infinity, we could rewrite this as the limit as u goes to 0. Right? And this should be a, well, hopefully be a nicer limit to wrap our heads around. We've definitely made the function itself nicer, okay? Because as u goes to infinity, well, e to the u goes to 1. So this is going to be 1 minus 1. So this part is going to 0. And then cosecant is 1 over sine. So 1 over sine of 0 is 1 over infinity. So this is a plus or minus infinity thing going on here. Okay, so this is a infinity times 0 case. Now, once again, since we have cosecant, we can fairly simply write this as a fraction by just writing this as 1 over sine. So we can rewrite this as the limit as u goes to 0 of e to the u minus 1 all over sine of u. And now we've made it a 0 over 0 case because, well, this part is still going to 0, but now sine of u as u goes to 0 is 0. So this is a 0 over 0 case, and we can now apply LHopitals Rule. Okay, so the derivative of the top is going to be just e to the u, and the derivative of the bottom is going to be cosine u. Now, I will admit, we don't have to do this rewrite, but if we didn't, we would be looking at this limit instead. E to the 1 over x minus 1 all over cosecant times 1 over x. And so we would be doing some pretty nasty chain rules here. But when we did, the chain rule would all have this negative 1 over x squared popping up in the top and the bottom, which would cancel out. And we'd still be left with just this. So you can also think of it as we'd have a u prime over a u prime here, which would just cancel out completely. Okay, so this really does simplify some problems. If you notice that you have some nasty stuff sitting around, but you could easily replace it all, right? It's actually a pretty good technique, right? It will simplify the problem. And now we can just plug in the 0, because we'll have e to the 0 over cosine of 0, which is 1 over 1, or 1. All right, so we've talked about the 0 times infinity cases. What about infinity minus infinity cases? These are going to apply in a lot of the same ways that they did before, where we use some algebra to get them to be something we're more familiar with. We use algebra to get them to become a 0 over 0 or infinity over infinity case. That's the same thing here. However, in this case, this is more useful for examples where we can't use algebra past this point, where there are things like natural logs or e to the x's or trig things. Okay, so to give an example of this, like a case where we can't continue to use algebra, would be something like the limit as x goes to 1 from the right of 1 over x minus 1 minus 1 over the natural log of x. This is going to be an infinity minus infinity case because as x goes to 1 from the right, 1 over ln x is going to be infinity, and then 1 over x minus 1 will also be infinity. This is an infinity minus infinity. Okay. However, it's fairly routine to move this into a fraction. We can just get a common denominator of x minus 1 times ln x and do a sort of cross multiplication guy to get that this is. And so using our algebra here, we will get the limit as x goes to 1 from the right of the natural log of x minus 1 all over x minus 1 times the natural log of x. And I'll go ahead and distribute that negative sign to get ln x minus x plus 1. Okay, and now what we've turned this into is a 0 over 0 case, right? When we plug in 1 here, you'll get 0 minus 1 plus 1, so 0 over, will be a 0 times 0. So this is now a 0 over 0 case, so we can actually apply LHopitals Rule and get down to the correct answer. So, using LHopitals Rule, I'll write my limit sign again here. Right, the limit as x goes to 1 from the right of, we'll have 1 over x minus 1, so that's the derivative of the top. On the bottom, we need to use the product rule. Okay, so it will be derivative of x minus 1, which is just 1, times ln x, plus x minus 1 left alone, times the derivative of the natural log of x, which is 1 over x. Now, this is still going to be a 0 over 0 case, because if we plug in the 1, we're going to get a 1 minus 1 up top, and then a 0 plus, and this x minus 1 will become a 0 again. All right, the 1 over x will become a 1. So we still have a 0 over 0 case. So we can just apply LHopitals Rule again. However, before we do that, I'm going to simplify the denominator a little bit to make it easier to take the derivative. So this will be 1 over x minus 1 all over natural log of x. And when you distribute this 1 over x, you'll get plus 1 over x. Oops, sorry. It's plus 1. The 1 over x and the x become 1 minus 1 over x. Okay, so now we can apply LHopitals Rule again. Okay, and so the derivative of the top, well, the derivative of 1 over x I'm just going to jump straight to that being negative 1 over x squared. And the derivative of the bottom, well, that becomes 1 over x. Derivative of 1 is 0, and then minus 1 over x, so we'll get plus 1 over x squared. All right, now remember, we are plugging in 1. All right, I went ahead and put in the limit sign just to keep us on track. And so now we should just be able to plug this stuff in and get an answer out, right? Because we'll have negative 1 over 1, all over 1 over 1 plus 1 over 1. So it looks like we are getting a negative 1/2. And there we go. Okay. Here's a case where our infinity minus infinity comes out to be a negative 1/2. So the start is still very similar to what we've done in the past. It's just some cases are going to require LHopitals rule once we get to that simplified form. All right, to show another example, let's say we have the limit as theta goes to pi over 2 from the left of tangent theta minus secant theta. All right, and whenever I see things like this, I sort of start by, I'll go ahead and rewrite these trig things, right? So tangent is sine theta over cosine theta, while secant is 1 over cosine theta. Now, here's where we will get our infinity over infinity, our infinity minus infinity, because theta, as x goes to pi over 2 from the left, that's going to cause cosine to be 0. All right, so over here, I've graphed a quick graph of cosine, and as we go towards cosine from the from the left side, cosine's positive, so this is going to be a 1 over 0 and a 1 over 0. So this is an infinity minus infinity case. However, I think it's fairly clear how we get this to be a fraction. Right? We have already a common denominator. This is going to be sine theta minus 1 all over cosine theta. And now we'll have a 0 over 0 case because sine of pi over 2 is 1. So we're going to get 1 minus 1 all over 0. So this is now a 0 over 0 case, which is what we need to apply LHopitals rule. Okay, so derivative of the top is going to be cosine of theta, and the derivative of the bottom will be negative sine of theta. All right, and now we should just be able to plug things in because cosine of pi over 2 is 0. However, sine of pi over 2 is 1. All right, so we will end up with 0 over negative 1, which is 0. Okay, there we go. So it may have been pretty clear here that these would cancel each other out since the sine theta is going to 1 here, but with LHopitals rule we can actually verify that. All right, so let's take a look at another example here. Let's say we have the limit as x goes to 0 from the right of cotangent x minus 1 over x. Okay, this should be an infinity over infinity because if we rewrite the way that this looks, right, cotangent is cosine of x over sine of x, and we'll have minus 1 over x. So when we plug in 0, this becomes a 1 over 0, and this becomes a 1 over 0. So we have an infinity minus infinity. And based on the fact that we're coming from the positive side for both of these should both be positive infinities that we're subtracting. Okay, if you ever get an infinity plus infinity, you don't have to go through all these steps because infinity plus infinity is not an indeterminate form. Okay, but from here we can get our fraction going. So we will have x cosine of x minus sine of x on the top and x sine of x on the bottom. And so when x goes to 0, this is now a 0 over 0 case. Right, so we can use LHopitals Rule. Okay, so when we take the derivative of the top, this first piece is going to require a product rule. Right, so it would be the derivative of the first, which is 1 times the second cosine left alone, plus x left alone times the derivative of cosine, which is negative sine. So I can rewrite the derivative of x cosine x as cosine x minus x sine x. And then the derivative of negative sine x will be negative cosine x. So up top the cosines cancel. That's nice. And then in the denominator, we'll have another product rule. Right? So it'll be sine x plus x cosine x. So let's simplify this a bit. We'll have negative x sine x up top, and sine of x plus x cosine x in the denominator. Now once again, this is going to be another 0 over 0 case. When we plug in 0, we'll get 0 up top and 0 plus 0 on the bottom. So we have another 0 over 0 case. So we can use LHopitals Rule once again. Okay, so the derivative of the top here, we'll need to use a product rule. So it will be negative x. Whoops. Sorry, let me do the derivative of the first. So it will be negative 1 times sine left alone minus x cosine x on top. Okay, then on the bottom, the sine of x will become a cosine of x, and we'll do another product rule here. So it will be derivative of x, which is 1, times cosine of x left alone, plus x times the derivative of cosine x, which will be negative sine x. So I'll make this negative x sine x. Now, I could understand that by this point, some of you may have been concerned that, oh, is all we're doing swapping back and forth, right? We're not going to get anything useful. And it turns out it looks that way, but not quite. This ends up being negative sine x minus x cosine x all over 2 cosine x minus x sine x. And now finally we can just plug in the 0, because sine x will go to 0, x cosine x will go to 0. However, the 2 cosine x, that cosine x goes to 1, and this part goes to 0. So the whole thing ends up going to 0 over 2, right, which is 0. So while it almost looked like we were just going to be switching back and forth, thankfully in the denominator here, that was not the case. Okay, so that is an example of our infinity minus infinity. Now, in the next video, so I'm going to go ahead and put a cut in the video here. Next video, we're going to look at the last form of the indeterminate forms that we have, and that's the ones involving powers, which we've talked about that before. Kind of follows in the same way. And we'll look at a couple of more complicated examples when we come back. However, this is definitely enough to get you rolling on most of the homework. The only things you might not be able to tackle just yet would be the ones involving powers. However, if you look back at your notes for limits in the past, how we dealt with powers, you might get an idea of how we would approach that, especially if you look at how we approach tower functions. Okay? Anyway, I will catch you on that particular video. Cheers.